Hello, everyone. So today we're going to be talking about how pressure can influence phase transitions. So in order to do this, we're going to go ahead and start in fairly logical place, same place we start actually with temperature, looking at how pressure influences chemical potential. And so essentially, if we go back to our fundamental equation of chemical thermodynamics, we'll note that um, pressure changes chemical potential or Gibbs free energy as a function of molar volume of the substance we're looking at. So this actually tells us a fairly cool thing. So if I'm going to increase the pressure of the system, as molar volume uh, has to be positive, it means that I'm going to increase the chemical potential of the system or essentially destabilize the system. So almost every system is going to become less stable under pressure. But the smaller the system is, the less it's destabilized by an increase of pressure. And this actually has some very important implications for phase transitions. So as we stated last time, if I have a phase transition, this is going to be the point at which my chemical potential for, say, my solid ends up matching up with the chemical potential of my liquid. Now, in general, most solids are actually going to be smaller than their liquid counterparts. So as I increase the pressure, the solid is going to go slightly up in chemical potential. And so what I do is I pretty much move my chemical potential curve with temperature slightly up. But liquids with their much larger volumes are going to be much more destabilized. And so their lines are going to uh, move up to a much greater extent. And what this does is it means that the new temperature of fusion or the new transition temperature is going to be much higher. So again, really illustrating that the smaller system is always going to be the one favored by increased pressures, which again makes sense. As I put the system under more pressure, I'm going to tend to confine its volume. And that's exactly what we see here. However, especially when we're looking at temperatures of fusion, it is important to make note that it isn't always going to be the case that the solid is smaller than the liquid. There are a few very notable exceptions where the solid has a greater molar volume than the liquid, most notably water. So in the case of water, ice is less dense than the liquid, which means as I apply pressure, I'm going to actually favor the liquid form of water over ice one. So again, we'll see a much greater increase in the chemical potential of the ice and a much smaller increase with the liquid. And what this does is it shifts the fusion point to a lower temperature, resulting in a decrease of the transition temperature. And so this is one of the things to watch out for. And you can actually see this when you look at the phase diagram uh, of water, because it has a negative slope when looking at the water-ice transition. Again, entirely driven by the difference in densities of the two systems. However, what sort of influence will external pressure have when I'm looking at a transition of a liquid into a gas, especially on the vapor pressure of the system? Because this raises a very important question of which is going to be the more important pressure, the vapor pressure or the applied pressure? A question that's been kind of dogging us all throughout thermodynamics. So we can analyze this by setting the chemical potentials uh, of my gas and my liquid equal to each other. And since we're looking under isothermal conditions, what we can then do is ignore the temperature contribution from each of these variances. And so the chemical potential of the gas is going to vary as RT over dP over the partial pressure of the system. And the uh, chemical potential of the liquid is going to be the much more traditional molar volume of the liquid times the change in the applied pressure. So again, one of the things I want to make note of is when I'm using P here, I'm applying to the vapor pressure. And when I'm using the big P, I'm referring to the total pressure. Again, the pressure felt by the liquid and the pressure felt by the gas, because these two will actually be different. And so let's figure out how this pressure felt by the liquid will influence the pressure felt by the gas. And so what we can then do is integrate both sides. And on this left side, RT is not going to show any pressure dependency. So what I'm going to do is integrate from my initial vapor pressure, say a reference condition such as 1 bar, to the actual ending pressure after I apply the additional force. And so what I can then do is essentially correct this form by saying that this is going to be equivalent to on the gas or on the liquid, starting with that initial vapor pressure. So this would be my initial pressure is going to be the vapor pressure applied by the gas. And then I'm going to essentially add in what additional amount of pressure is going to be required to essentially increase the partial pressure of my gas. So again, we can integrate the right side over this new variance. And again, we're going to, since this is a liquid, assume that the volume is relatively indifferent to the amount of pressure being applied. So by pulling that out, we end up simplifying the integral on the right side. So the left side integral essentially is going to simplify to the natural log of my vapor pressure over my initial vapor pressure. I'm going to go ahead and move the RT over to the other side. So I'm going to have the ratio of the molar volume over RT times essentially the difference in pressure, as the vapor pressure will end up canceling out in the integral. So this gives us a way to relate the pressure felt by the system to the to how much applied pressure is how much pressure is applied. And again, what we can then do is, if I know the vapor pressure of the system, I can move that to the right, and I can figure out how much greater is the vapor pressure going to be over my initial vapor pressure by essentially adding extra force. And it turns out that for most cases, this is actually going to be fairly minor. So for example, if I'm looking at water and I apply an additional 1 bar of pressure. So say I start at the initial vapor pressure of the system and I apply an extra 1 bar of pressure, it turns out that we end up within 0.07% of the right answer. So essentially, when I'm looking at how much the ratio of pressures changes, it changes by 0.07%. So again, any influence of atmospheric pressure tends to be fairly minor on the ending vapor pressure. So as a result, when we're talking about vapor pressures, we often ignore the influence of extra applied pressure. So specifically, this is going to come into play when I'm looking at liquid gas and solid gas transitions, as it's going to have a fairly minor influence on the vapor pressure. That said, make note that if you're applying large external pressures, say on the levels of kilo or megabars, you are likely going to have to take into account that the vapor pressure will actually be much higher than predicted by some of the equations we're going to work through in the subsequent slides. So again, make note that this does play a role, but it's often such a very minor one. However, when we're looking at solid-liquid phase transitions, the pressure that we're going to be talking about is almost going to be exclusively the applied pressure or force put on the system, not just the force applied by the gas itself. So again, this is a notable difference when I'm going to be throwing a lot of P's around in these slides is the difference in between partial and applied pressures. So let's go ahead and try and extend this to a little bit more general of a system. So I want to go ahead and try and describe a more general phase boundary in between two phases, alpha and beta. So uh, they may be liquids, gases, solids, or different allotropes of a two different solid phases. So again, identity doesn't exactly matter. However, what I do know is that the chemical potential of both of these phases is going to show a dependence on pressure and temperature, as has already been demonstrated. So how am I going to essentially predict how these pressures and temperatures are going to interact? Well, one way of doing that is to insert our fundamental equation of chemical thermodynamics. So we're going to show a variance on temperature and pressure for the alpha phase and temperature and pressure for the beta phase with coefficients of the molar entropy and molar volume for each of the corresponding phases. So as we've seen before, it's often a little bit hard to try and simplify a system like this where we have mixed variables on each side. So we're going to go ahead and move all of our pressure terms over to the right. So what I'm going over to the left, technically, is I'm going to subtract the molar volume of alpha by both sides. I'm going to add the molar volume of beta to both sides. And so when I do this, I'm going to have a molar volume term looking at the pressure dependency and a molar entropy term describing the temperature dependency. So what you may notice is that this molar volume term is product minus reactant. Ta-da! This is going to be the change in molar volume for the transition. And similarly, on this right side, we have the change in molar entropy for transition. So what we can then do is rearrange the system. I'll go ahead and divide both sides by dt and by the change in molar volume of transition. And this generates something called the Clapeyron equation. And this is actually a fairly useful expression as it's going to show how the pressure, whether it's vapor pressure or applied pressure of a system, changes with temperature. And this is actually a fairly useful expression. And it turns out that the variance is going to be related to how the molar entropy changes and the change in volume of the system. However, one of the things that's worth noting is that as chemists, we often don't like playing around with terms of entropy. So instead, what we often do is we substitute the change in entropy of transition for the enthalpy of transition, remembering that the entropy of transition for an equilibrium system, which again a phase transition is going to be the same as the enthalpy of transition over temperature, generating our new expression. So what this does is it lets me describe the change in pressure with the change in temperature over the enthalpy of transition, the temperature of the system, and the change in volume. Now, you're going to notice there's going to be a couple little problems here. For example, I'm looking at how pressure changes with temperature in terms of temperature. And also, as we've seen previously, the change in volume of a system is going to be heavily dependent upon what sort of phase transition I'm looking at. So from here, we're going to have to subdivide how we treat the Clapeyron equation in terms of what system I'm examining. So let's say I'm examining a nice solid liquid phase transition. So this is going to give me a transition of fusion. And it's worth noting these same principles will apply for solid-solid transitions if we're looking at a change in between two allotropes such as diamond and graphite. So what I'm going to then want to do is move my temperature expression over to the right, helping simplify my expression. And then I'll go ahead and take the integral of both sides. So I'm going to take the integral from some reference condition. So oftentimes this is going to say be standard states. but very typically it's going to be some point that's well known on the curve. A triple point is often a good reference point for the system. So I can then examine the change in pressure, which is going to make a fairly simple integral. But over here on the right, I'm going to want to pull over the terms that we're going to treat as non-temperature dependent. So we're going to generally treat the enthalpy of fusion and the change in volume as non-temperature dependent. In truth, if you need high accuracy curves, you are going to want to treat both of these expressions as showing a temperature dependency. However, this often relies on the use of um, advanced techniques such as as Kirchhoff's law, such as we've talked about earlier in thermodynamics. But from this simple first approximation, we can then uh, pull these two terms out, and we're left with our good old-fashioned integral dt over t. So when we do this, we get a change in pressure term on the right, a ratio of enthalpy to volume, and a natural log of the difference of temperatures of the systems. However, we're going to likely want to end up simplifying this expression a little bit. And from here, we're going to make use of some mathematical identities. Specifically, what we're going to want to do is simplify this natural log of the ratio of the two temperatures. So in order to do this, we're going to use a trick where we essentially add one inside of, or we add 0 inside of our natural log term. And we're going to do this as adding our reference temperature over itself, so 1 minus 1. So again, we're allowed to add 0 anywhere we want because it's always there. However, when we do this, it lets us rearrange this natural log expression, because what we can then do is pull this expression of 1 out front, and then I can combine these two terms as T minus T prime. So the temperature minus my reference temperature divided by the reference temperature. Well, this might seem like a little bit of a why did I do that? But it turns out that there's a fun mathematical identity that lets us express the natural log of 1 plus x as x plus 1/2 x squared plus 1/3 x cubed. Essentially, it's a nice Taylor expansion that helps describe the natural log of a ratio. So more or less what we're doing is we found a good way to get rid of the natural logs. However, when we have values, when we have values of temperature differences that are relatively small, well, it turns out that this second expression more or less drops down to 0, and I can treat the natural log of t over t prime as t minus t prime over t prime. And again, remember that this will only hold for relatively small temperature differences, but as we'll see, this is often the case when looking at how temperature changes with pressure. As you've often seen with as we've seen a little bit at the end of thermodynamics, the temperature of a phase transition often changes very slowly with comparison to the change in pressure. And so we can then back substitute in this expression, and what I get is the change of pressure with reference to the change in temperature over the reference temperature, which you can go ahead and see here. And then we can also essentially define this. If I'm looking at what my final temperature is, if I know a reference temperature, it's going to be based on my reference temperature conditions, and again, the difference of the temperature of the system. And again, it is worth noting that this does rely on the fact that my initial temperature is relatively similar to my reference temperature, which is very often the case. So this is actually a fairly good approximation. However, we're not just interested in how condensed phases interact, we're often interested in how uh, uh, in the vaporization of a liquid or also of a solid. This proof will actually apply to both. So we're going to go ahead and start with the idea of, again, of the Clausius equation, and we're going to essentially form what's called the Clausius-Clapeyron equation. So the whole idea with this expression is going to be if I'm looking at the change in volume for a vaporization reaction, well, it turns out that relatively my solid or my liquid has very little initial volume compared to my ending gas. So I can treat this, the volume of my product species as just as the entirety of my change in volume. So essentially, if I start at 0, my final condition ends up dominating the change in volume, which lets us make use of the ideal gas law, because I can then substitute in RT over P for my volume term, which we can then end up simplifying the whole bottom expression as RT squared over P. And so then we can go ahead and move my temperature terms over to the right and my pressure terms over to the left. Now, one of the things that's worth noting is when I multiply the 1 over P on both sides to eliminate uh, this P in the denominator and putting it over here on the left, it turns out that 1 over P dP is going to be the same as the derivative of the natural log of P. So again, this should hopefully make sense because we've done enough expressions of dP over P to notice the high degree of relation to the natural log of pressure. So what we're going to then do is by isolating my natural log of pressure on the left and my temperature expression on the right, I can then go ahead and integrate over both sides to try and see how my pressure changes with the temperature. So when we do this, what we're going to find on the left is that our good old friend, the derivative of natural log of P, is going to become the natural log of final over initial conditions. Now over here on the left, we're going to assume that our enthalpy of vaporization is going to show no temperature dependence, and we already know that R is a constant. And this leaves us with the integral of dt over t squared. Well, this is going to give us an integral of negative t, and in the definite form, this gives us negative over 1 over t squared minus 1 over t2 minus 1 over t1. So essentially, the change in the difference in our inverse temperatures. However, one of the things that's worth noting is we're often interested in how pressure changes over and change in temperature. So we often like to remove the natural log on the left side, so we raise both sides to the exponential. And so this gives us the ratio of the pressures equal to the exponential of the negative of change in enthalpy over R times the change in the inverse temperatures of the system. And again, if you're trying to determine the final pressure of the system, you can essentially, again, rearrange the sets of equations. So hopefully this ends up making mathematical sense of how the pressure is going to end up changing with temperature. It's going to show a relatively exponential behavior. And again, worth noting that this applies for both sublimation and vaporization. So if I'm looking at a general phase diagram, hopefully these equations will go a long way to describing the shape of these lines. What we tend to see is we see a exponential behavior when we're looking at our sublimation curve and our vaporization curve. And because the enthalpy of vaporization is often so much more positive or less favorable than the solid vaporization curve, it's the reason why you start to see when you start to see a major change in the solid and then it goes over to the liquid, we see a much slower exponential growth indicated by this much more positive enthalpy term or lower value. Similarly, we see a straight line when we're looking at our fusion, the phase boundary for fusion, as we see a relatively linear relationship when looking at temperature and pressure for solid liquid phase transitions. Now, again, one of the things that's always worth making note of is that you can tell a lot about the solid and the liquid by looking at the direction of the line. If we see a positive relationship in between pressure and temperature, this means that my change in volume is for fusion is indeed going to be positive, in helping indicate that we're going to favor the more dense species, often the solid, at higher temperatures, which we see here. However, watch out for the notable exceptions because sometimes we're going to see a negative line here as the liquid is going to be more dense than the solid, the most notable case there being ice. But again, it is also worth noting that this diagram is slightly exaggerated as the change in pressure with temperature is often so small that this line may look relatively straight up until you go to very high pressure conditions. So hopefully this helps explain a lot about the shape and behavior of phase transitions and phase diagrams. So next time we're going to go ahead and wrap up this chapter by talking about a few quick definitions of some odder behaviors when looking at phase transitions. Next time, air and fast classifications of phase transitions. Till then, take care.